In this video, we're going to discuss what happens in Le Chatelier's principle. Le Chatelier's principle essentially is worried about a stress on a system at equilibrium. So at equilibrium, this forward reaction is equal to this reverse reaction. Collision reaction theory suggests or tells us that these particles are colliding and successfully reacting at the same rate as these particles are reacting and colliding to go the opposite direction, so that the forward reaction is equal to the reverse reaction. Now, that's essentially equilibrium. It's at equilibrium when it's in these flattened regions of the graph, and it reaches equilibrium again here. Because this is concentration, and we know that the equilibrium constant for this will be the concentration of carbon dichloro, methane, and then hydrogen chloride gas squared over the hydrogen fluoride gas concentration squared. And so it's all related to equilibrium concentration. Now, the hydrogen fluoride here, you can see, has been suddenly added. So it's at equilibrium, and somebody's injected this. If you add the hydrogen fluoride, there are going to be more collisions of the reactants. So you're going to increase the amount of forward reaction, which is going to use up hydrogen fluoride. That's why its concentration decreases. And then it's going to make more of the reverse reaction, or more of the forward reactions. So more of these products are being made. So their concentrations, relatively speaking, go up. The reactions, though, eventually will even out, because eventually once these concentrations, once the product concentrations increase enough as they go up, they're going to have more of these reverse reactions until they re-establish this equilibrium. And so that's what's happening here. They've added a chemical and it's being used up to make the products. So that's our essential Le Chatelier concept of just adding something. Now, alternately, if you were to remove something, so if they were to remove the hydrogen chlorides, so here you've got it all at equilibrium, but now they're going to remove this chemical, then its concentration suddenly goes down, like it does in this part here, and the forward reaction is again going to be favored. There are fewer of these to actually do the reverse reaction, so it's going to drive the forward reaction to produce more of the products, and this chemical, since it was never removed, just keeps increasing. So it's a way to make more Freon 12, just removing the hydrogen chloride gas. But the hydrogen fluorides are going to get used up. Eventually, the two relative equilibriums are going to be, or the forward and the backward reactions are going to cancel each other out again. So if we add something, we need to use that chemical up, forward reaction. If we remove something, we need to replace it, and so it increases the reaction rate of the reaction that's going to replace that chemical. If instead we had a graph that looks like this, you can see that in this case the reactants, which are here and here, at equilibrium are suddenly starting to be used up, and the products are being increased. And so in this case, what this suggests to me is that the energy here is being removed. The system is being cooled, because if you cool it, cooling removes energy, and it's going to force the reaction to replace that energy, and it will increase the forward reaction until it makes a new equilibrium and flattens out. But in this case, the Kc will actually change, because in this case we're increasing the concentration of products, and we're also decreasing the reactants. And that's happened in the past, but it followed adding something in. In this case, we're just affecting the energy, which has no relationship to this. So by removing the energy, it forces the reaction to go forward. If instead they'd heated this up, it would force the reverse reaction, and we would see these concentrations go up and this concentration go down. So commonly, if you see the reactants all increasing and the products decreasing, or the products increasing and the reactants decreasing, and there was no sudden changes, no addition of a chemical like we had in this graph, or removing of one chemical like we had in this graph, that suggests to us that it's an energy change. Okay, so if you've got reactants doing the exact opposite of the products and there is no other obvious change, it's probably energy change. So here we've got a different system though. Look, in this case, the concentration of this gas increases, and this gas increases. Since all the concentrations increase, it's telling us that they've compressed this. So this is decrease in volume or an increase in pressure will cause this increase in concentration. And in this case, because they've increased the concentration, we've decreased the volume, it's going to favor the side with fewer particles. So we're going to see that more sulfur trioxides are being made, and these are being used up to re-establish equilibrium. Kc will be the exact same for this. So that leads us kind of to this graph, and I'll go through this graph with you quickly. I guess I haven't run it too long yet. So here you can see that we've got a sudden decrease in all concentrations. So if it decreases concentration, that sounds like an increase in volume to me. An increase in volume would favor the reactants, and so we see that the reactant molecules are both increasing here and the products are being used up. So this was an increase in volume, and that all of the chemicals are all decreasing concentration suggests that. Over here you can see that I've got the reactants going up and the products going down. And like I'd said earlier in the video, that suggests that this has to do with energy. So there were no sudden changes in anything, no like vertical lines like this. So when you've got opposite change happening, and I'm making more of the reactants, they must have heated this reaction vessel, because by adding the energy, it's going to favor the reverse reaction until it reaches equilibrium again. Here, this is a dead giveaway. You can see a straight vertical line. They have added the ethane molecules to it. And here, the change that's occurring, perhaps no change at all, looks to me like they maybe have added a catalyst. Catalysts will speed up reactions, but they don't affect the equilibrium position at all. Hopefully that helps you understand these graphs. Le Chatelier's principle is always working on the core concept that if you do a change to the reaction, so create a stress on it, it's going to do the opposite. So if we removed this, it needs to replace it. If I added this, it needs to use it up. If I added this, it needs to use it up. And then understanding how the graphs relate to that is sort of the key to Le Chatelier's principle.